We are unmuted. We are recording. Fantastic. All right, guys, we are in. Oh, we've been in the home stretch. We're almost at the end now. This is our second to last class meeting, other than the final. I know, right? Isn't that sad?
So sad.
It is. No, I'm serious. I'm not being sarcastic. Yeah. Since we didn't get to meet very much last semester, I've really enjoyed getting to work with you guys this semester. So I'll be over soon. Take a moment here. All right, that's enough moments. Let's get back down to business. Okay, guys, let's go ahead and pick up where we left off in chapter 22. I believe the last thing we talked about in chapter 22 was we started talking about reactions of carboxylic acids. And I think we went over the formation of acid chlorides reaction. Am I correct? Okay. All right. Okay, so there's a couple of other reactions that are going to be noteworthy with acids. All right, the first one's called Fischer esterification. You can probably figure out what we're making here, I hope. What are we trying to make? An ester, yeah. This mechanism, this reaction is very, very similar to one that you guys learned back in chapter 21. This one is very similar to the formation of an acetal. Of course, the big long mechanism, right? Of course. All right. But yeah, this is one of the most common ways of making esters. Used a lot in various types of industrial applications. It can be even used for formation of polymeric esters, polyesters, such as are found in certain types of clothing and other applications. Let's see how you do it. All right, so to do a Fischer esterification, you need a carboxylic acid. Just like the acetal formation, it's actually an equilibrium reaction. You need an alcohol, and you need a strong acid catalyst, such as sulfuric acid. Even the setup looks very, very similar to what we did with acetals. Okay? And if you remember the mechanism for acetals, and I hope you do, since it was on the test yesterday and the day before, or else it's maybe already left your mind. Yeah. But if you remember that mechanism, you can probably figure out a large part of this one. Like I said, it's really, really similar. All right. So look at this. Any ideas how we're going to start things off? If we're looking for parallels. Yeah, same thing as before, right? Previously we saw the acid begin the reaction, all right, by protonating the carbonyl oxygen. Same thing happens here. And in fact, just like acetal formation, this one kind of has two phases. Each phase is indicated by, is started by the action of the acid and ends with the reformation. So, yeah, a lot of parallels. All right, so it gives you a protonated carbonyl. Then what do you think happens? Well, the point of protonating that carbonyl oxygen, yeah, makes the carbonyl carbon more susceptible to attack, and that's where that alcohol comes in. Make an attack right there. Driving a pair of electrons up. And you see a whole lot of oxygens attached now. And you have one more step in phase one. What's that going to be? Mm-hmm. Exactly. HSO4 minus swoops in, grabs that H, and you're at your halfway point. So at your halfway point, you have this one carbon that's got two OH groups and an OR group. So there's a lot of stuff going on. And you also reform sulfuric acid. Okay. So we are halfway there. All right, then we begin phase two. How does phase two begin, do you think? Well, each phase has to begin with H2SO4 doing something. What do you think it's going to do? Yeah. It's going to donate a proton to one of your OH groups. Doesn't matter which one, they're both exactly the same. It's going to give you that. Then what? We just made water, right? Water leaves. Try to maximize my board space here. Let's see. All right, so that leaves you a carbocation. All right. Now, like we've seen before in one of our other mechanisms, we can actually draw a resonance structure here. You can draw a resonance structure by having this pair of electrons come down, form a carbon-oxygen double bond. And now you see this is looking a lot more like an ester. What's the last step in the mechanism? HSO4 minus comes back, deprotonates this guy, and boom, you have your ester. I didn't mean to draw through the O there, but I think you guys can still see it. Okay, so yeah, like I said, very, very similar to what we did last chapter with acetals. Are there any questions about how we did this? Does that make sense? Carboxylic acid, one equivalent of an alcohol, and then a strong acid catalyst. By the way, just as a funny little aside, you have to get the temperature up really high on these reactions to get them to work efficiently. On more than one occasion, I've done this in the past in a lab. You know those blue Keck clamps that hold your distillation glassware together? on a couple of occasions, it's caused those to melt. Yeah, so those little blue flames, they're just like big, long, drippies of plastic. And that's how hot these reactions get sometimes. Still see a couple people running, so I'll stall. Say that again?
Oh, in the bottom right.
Bottom right?
Those alcohol groups are always going to be identical.
Yeah, these two OH groups are exactly the same. Yeah. So it doesn't, and if you're drawing a mechanism, it doesn't matter which one you draw the proton going to. All right. Can I erase? I know this is kind of a long one, so I'll make sure. All right, so that's how you convert an acid into an ester. All right, you can also convert acids into amides. And we're going to use something called DCC. Now, please don't get that confused with PCC. That does happen sometimes. Understandable. But this is DCC. DCC, I think, stands for dicyclohexyl carboxydiimide, or something to that effect. I'm going to draw the structure in a second. Honestly, I hate doing this mechanism because DCC is big, and you have to draw that thing over and over again. So I'll be glad when this one's done. Hopefully I'll have enough board space. But it's actually pretty simple. All right. So there's actually a couple of different ways that you can make amides with acids. There's another one that's a little bit simpler where you just basically take an acid, you add an amine, and you heat the crap out of it. And it will eventually make an amide. The thing is, though, it usually gives very low yields. So it's not a very efficient method. It's not very practical. It's not used very often in real world stuff. So I'm not going to bother going over that. The more important one is to look at this. The more important one is this one, where you actually use something called DCC to sort of help you out. All right, so let me show you how this works. All right, so you have your acid, and by the way, this can be used to make primary amides, secondary amides, or tertiary. It can be used to make all of them. If you want to make a primary amide, use NH3. If you want to make a secondary amide, use a primary amine. If you want to make a secondary amide, use a tertiary. Wait, no. Let me back up. Primary amide, NH3. Secondary amide, primary amine. Tertiary amide, secondary amine. I got a little jump on there for a second. All right, for our example, let's just go ahead and we can make a secondary amide here using a primary amine. All right, so you need the amine, and you also need this compound. This is DCC. See why it gets a little cumbersome to draw in the mechanism. Kind of large, but does its job very well. All right. I don't know if y'all remember the acid chloride formation that we learned a couple of classes ago, but this has a similarity with that. Excuse me. We need to make this into a better leaving group before we can do anything with it, right? So we're going to use DCC and actually start off this way. Your acid OH is going to attack the carbon of DCC, that middle carbon. All right, and when it does so, it'll knock a pair of high electrons to one of the nitrogens. Cutting off some of my line here so I can get all the structure in. Okay. So it gives you this. Okay, so remember the point of this is to make OH a better leaving group. What's the next step? Any ideas? Just from looking at what you got? The whole thing doesn't leave yet. There's something else we got to do to the group before we start trying to make it leave. Yeah, how do you satisfy the charges? Yeah, exactly. Negative nitrogen, positive hydrogen. Let's just have that hydrogen hop on over to the nitrogen. And now we're ready to set this up to leave. Okay. All right, so now we're ready for attack. All right, so now's when your amine's going to come in. Your amine's going to attach itself right there. Attack your carbonyl carbon. And that's going to cause this group to leave. As it leaves, it kind of does a reshuffle. This pair of electrons is going to travel over here to make a carbonyl. And that'll cause a pair of electrons over here to go to the end. Okay, so that's going to give you something that looks very similar to an amide. It's just a protonated amide. Bless you. And now this group is off to the side. All right, one more step of the mechanism. What do you think it is? Again, we got a couple of charges. Let's just do a proton transfer and that'll satisfy both of them. So you can see here, your final product is an amide. Specifically a secondary amide in this case. And then we also get, ooh, I might draw this little, we also get this. As a byproduct. This is the most important part. Can't believe I got that all in that little board space. I'm proud of myself. But yeah, like I said, you can use this to make primary or secondary or tertiaries. It just really depends on what's on the other side of this nitrogen. If this was just an NH3, you know, then that would translate to having an NH2 over there, for instance. And this is much more efficient than the other method I mentioned, the one without BCC. This gives you a much, much better yield. So this is going to be industrially, certainly, the preferred way to do it. Okay. A couple of you are still writing. Any questions about this one? You know what's kind of nice? I guess, you know, I know you guys aren't exactly looking forward to the standardized multiple choice test. Hey, why would you? But here's one good thing. You don't have to, from memory, try to do all these mechanisms. Although it is so good to understand how they go. But you won't have to recite an entire mechanism. All right, can I erase? All right, one last thing about acids that's kind of cool. You can only do this in certain situations. You can actually make cyclic anhydrides. From acids. And specifically, you have to have diacids. That means you have to have a molecule that's got 2 carboxylic acid groups. All right, so let's say you had something like this. I drew it kind of like that to make it a little bit easier to visualize. But yeah, that's a diacid. Got 2 carboxylic acid groups. You can actually convert this into a cyclic anhydride. Gives off water in the process. You know how you do it? You heat the crap out of it. That's all you do. That's it. I don't know the mechanism, so I'm not going to show it to you. But suffice it to say, this works very well. One cool thing that happened one time I was teaching a polymer chemistry class, and we had a lab. And for the lab, we needed maleic anhydride. I go to get the maleic anhydride off the shelf, and whoops, apparently I had misread the label. We didn't have any maleic anhydride. We had maleic acid. Right? So that's an oh crap moment. But maleic acid is actually a diacid. And so what we did, we took some of that maleic acid in class and we heated it over a Bunsen burner in an evaporating dish. And it was really cool. These were these sort of granular pellets, and this long stringy stuff started to develop. Looked just like cotton candy. So literally we got string rods, and we wound and wrapped this maleic anhydride as it formed. And we have this big white cotton candy looking ball sitting on our stirring rod, but it was maleic anhydride. And then we were able to use it for our other stuff. So kind of cool. Right? This is very situational though. This can only be done to make 5 or 6 membered rings. Does not work very well to make 4 or 7, anything bigger or smaller. Any guesses why? 2 words. What's that? It is not steric hindrance. 2 other words. Dealing with cyclic compounds. Angle is one of them. Angle blank. Strain, there we go. Yeah. If you try to do this and make like something bigger or smaller than 5 or 6 member rings, you end up with too much angle strain, and it's just not stable enough to form. So, you know, like I said, kind of situational, but very, very useful sometimes if you need a particular 5 or 6 membered cyclohydride. All right. That is it for carboxylic acids. Any questions? All right. Let's talk reactions of esters. Really, there's only a couple of reactions of esters that we use a whole lot here. And they're both examples of hydrolysis. Okay? We can use water to break apart esters, and we can do it in a couple of different ways. I'll show you first doing an acid hydrolysis. Do y'all remember back in chapter 21, we learned how to make acetals, and then we learned how to hydrolyze them, basically do the reverse? That's what we're doing here, but with Fischer esterification. This is basically the reverse of Fischer esterification. All right, so you got your ester. We're going to have a strong acid. Again, sulfuric is a good example of this. And what else do you think we're going to need? What's the missing reagent on top? Lots and lots of water. Yeah. Let's use lots of water. I bet you guys could figure this mechanism out on your own. Let's see if we can do it together. What's the goal here? Well, we want to make the original ingredients of a Fischer esterification. So we want to end up with a molecule of a carboxylic acid, and we want to end up with a molecule of an alcohol. All right, so let's see how we go about doing it. All right, how do you think we're going to start off? Mm-hmm. Same as before, right? Acid's going to protonate your carbonyl oxygen. All right, now what? We got protonated carbonyl oxygen. We've seen this a few times before. What does that do to the carbonyl carbon? Mm-hmm. Makes it more, what was this? What'd you say?
Reactive.
More reactable? Yes. Is that what you said originally? You're trying to smoothly cover it up for you. No. More reactive, yeah. All right. What can react with your carbonyl carbon here? Water. Yeah. So water comes in. That's carbonyl carbon. Drives a pair of electrons up. Next step. HSO4 deprotonates. And lo and behold, you see we end up at the exact same halfway point we did. We got to in Fischer esterification. That makes sense, right? We're just going backwards, so we should hit the same halfway point. Right? And that's going to be the end of the first phase. Right? Now we're going to begin the second phase, right? We said the phases always begin with action of the acid. What do you think the acid is going to do here?
Put in the O by itself.
What's that?
Put in the O by itself.
You mean an OH or an OR? OR, yeah. The H is going to protonate that one. All right. Now, last time we did this, last time we were at the halfway point here, we didn't protonate this O. We protonated an OH instead. Why not protonate an OH this time? I want to remember that one. The French dude's principle. Le Chatelier? Yep. Yeah, Le Chatelier's principle. Right? If we protonated OH, we would give off water. We've already got a bunch of excess water, so we don't want any more. So it's going to go over here instead. Right? That produces an alcohol that can leave. Right? Once it leaves, it's going to leave behind a carbocation. And actually, that alcohol that left is one of your products. So I'm going to put a rectangle around it. All right. So you know one of the products should be an alcohol. We got that. Another one should be a carboxylic acid. All right. Carbocation here. We can draw a resonance form. When a pair of electrons swoop down from oxygen. And then the last thing we have to do is deprotonate this with HSO4 minus. And boom, we have our carboxylic acid. So yeah, literally the reverse reaction of a Fischer esterification. Very, very similar to the reverse acetal reaction. All right. Stalling, so people can write down. Are there any questions about how we did this? Does that make sense? Can I erase? All right, so that is how you hydrolyze an ester in acid. You can also hydrolyze it in strong base as well. And you're going to like this one because this one's a lot simpler as far as the mechanism. All right, so when we do this in base, that traditionally means that we have hydroxide ion, presence of hydroxide. All right, instead of a strong acid. All right, so OH minus is a lot different than water. It's a lot stronger of a nucleophile than water, right? So it's not going to need any help to come and attack this carbonyl carbon. It's strong enough just to go ahead and attack. All right, and this is going to be a straight up substitution. That means this group, that OR group, is going to leave. So that produces a carboxylic acid and an OR minus group here, in this case, O ethyl minus. Now, one thing about this species right here, any OR minus, is pretty strongly basic. So you have a pretty strong base here. This is a carboxylic acid. So something can actually happen with these two. What do you think is going to happen? That's a carboxylic acid. What do acids like to do in general? According to the Bronsted definition. Get rid of a hydrogen. If there's a strong enough base to accept it. Is there? You betcha. So what happens is actually, once you form this, that OR minus will steal a hydrogen from your acid. And as far as the final products go, you don't end up with a carboxylic acid. You end up with a carboxylate ion. And an alcohol. So the end products are slightly different depending on whether you hydrolyze something in acid or base, right? If you hydrolyze an acid, you get an alcohol and a carboxylic acid. If you hydrolyze it in base, you get an alcohol and a carboxylate. Does that make sense? This is actually a pretty good reflection of what we can actually see in some biochemical processes. All right, I think I mentioned way back in organic one. This may be way out of memory banks by now. I think I talked about making the old way of making soap. Maybe, kind of. Zan, you're saying nodding. Yes, you remember that far back. Yeah. Remember how people used to make soap? What they used to make soap out of? What's that? Animal fats. Yeah. You get all the fat scraps from the butcher. You toss them in a big cauldron. Pour a bunch of lye, aka sodium hydroxide, in there. Stir, stir, stir. Heat, heat, heat. Eventually, you make soap. Right. Well, that illustrates this process very well. Think about it. All right. We have our animal fats. All right. Have you guys ever heard of something called triacylglycerols? No? Have you heard of triglycerides? Ah, so where have you heard of that? Probably you ever had a cholesterol screening, you've probably seen had your triglycerides checked. Triglycerides and triacylglycerols, they're the same thing, it's just two different things. That is the major way that animals, including humans, store extra fatty acids. Basically what happens is, this is bonus biochem knowledge for you, by the way. Also means I have less time to teach you new mechanisms, so I'm going to take that and for what you will. All right, that molecule is called glycerol. All right, it's a triol. And basically what happens, it can take a bunch of fatty acids. And basically it stores excess fatty acids by combining them with these OHs and making esters. Put an extra O in there when I didn't need to. And this is a triacylglycerol, aka a triglyceride. Oh yeah, so if you consume a bunch of extra fatty acids, this is how it's stored in the body. This is fat, as you kind of think of it in a normal, everyday vocabulary, right? Now, so you think about collecting all those animal scraps, you have a bunch of this. You have a bunch of ester linkages. You have 3 in one molecule. So whenever you toss it to the cauldron, you put your lye or sodium hydroxide in, that, as we just saw in the last mechanism, breaks those ester bonds and frees the carboxylate groups from it. And when it does, it makes a fatty acid salt that actually basically serves as the soap. So kind of cool and kind of disgusting to think about all at the same time. I ask this every year. Every year I'm surprised people say yes to it. Have any of you seen the movie Fight Club? Okay, let me get this out of the way. Yes, I know the first rule of Fight Club is don't talk about Fight Club. All right, but do y'all remember the scene where they go to the liposuction clinic and steal a bunch of the fat from the back? They're making soap out of it, right? Making soap out of human fat. Wouldn't you like to do? You just wash your hands with a bar of soap made out of human fat. Kind of disgusting thinking. Yeah, Grady, you're like, oh yeah, bring it on. But I mean, that's how it used to be done. Not with human fat, but you could do it. So. Another old name for this is called a saponification. Again, you don't really need to know that, just extra information. Sneak peek of biochemistry. Triacylglycerols in the body are broken down. You need some extra energy. You need to free some fatty acids in the body. Fat cells can be broken down, right? So these molecules can be broken down. Now, you don't have free sodium hydroxide running around in your veins or body or anything. That would be really bad because you would die. But that's actually an enzyme catalyzed reaction. It's catalyzed by an enzyme called lipase. But industrially, we would do this with sodium hydroxide. So kind of cool. All right. Are there any questions about reactions of esters? All right. Reaction of amides, not worth going over. It's not, because amides are terribly, terribly unreactive molecules. It is possible to turn amides into carboxylic acids, but again, it's a very difficult process and it gives you a very low yield. So, kind of a waste of time. All right, so the very last group we have to talk about is nitriles. What I think I'm going to do is I'm going to hold off on that. I'll go over briefly on Monday, and then we'll use the rest of Monday for any questions you guys might have about the final exam. Okay? Any questions about anything we've gone over?
What is the HNMR lab stuff do?
HNMR, get to me by Monday. Okay. If you have it written on paper, just be sure to take a photo or something of it and either share it with me on Google Docs or email it to me. Again, make sure everybody in your group has their name on it, or else somebody is going to unfortunately get overlooked. Okay? All right. Oh, one other thing I've been needing to ask. On quiz 8, that was the one where I gave the whole class bonus points if you got something right. Of course, I don't know where it is. Now, somebody did not put their name on the quiz, so I don't know whose it is. So somebody's sitting with a 0. It looks like girls' handwriting, but I'm not sure. So if you're wondering, if you're missing quiz 8 score and you think you were here, come and take a look at it, see if it's yours or not. Also, one last thing. I think the window confirmed this with me if you know. Have you guys gotten the link yet to complete idea evaluations? Your student evaluations? Okay, let me talk about these for a second. Idea evaluations are used to, of course, evaluate your experience, your opinions of our courses. These are pretty important. Not only are these used a lot of times in sort of yearly assessment of employee performance, they're used to determine raises. They're used to determine promotions, that type of thing. The more participation we have in them, the better, right? Last semester, I think like maybe 20% of the class, if that many, filled them out. So we're looking to try to get more people to fill these out. All right, so I would like you guys to do that. I'm going to give you some motivation. If we get at least 80% of the class to fill out their ID evaluations, if you're doing the math, that's going to come out to be about 22 people out of the 27 that are enrolled. If we get to 80%, I'll drop an extra quiz grade. Yes, so there's some motivation to kind of get those filled up. I also highly, highly encourage you to fill them out for other classes as well. I know it's just another thing to do. I know you like to see, oh, survey, I don't want to deal with that. I feel the same way about surveys. I get an email, but it is important, right? So please, if you will, fill those out and encourage your classmates to do so as well. I'll be keeping an eye on the totals, and I'll let you know if and when we get there.
When should I have that?
Good question. I don't know off the top of my head, but they should have told you like in an email or with a link or something like that, all right? So there you go. That's all I got. So I'm going to give you a few extra minutes of your lives back. Any questions? All right, cool.